professional as I can here, you know.
Okay, I understand. I almost never wear a jacket back home, by the way.
Not until I moved to the D.C. area.
Yeah, there it seems to be mandatory.
Yeah.
I feel these young people running around in coats and ties.
Right.
Oh man.
Growing up in California.
Not like Berkeley.
Yeah, right. Good. Maybe you can just start by introducing yourself.
My name is Philip Lubin. I'm a professor of physics at UC Santa Barbara.
Okay. So what brings you here to the 2013 Planetary Defense Conference?
So I was in Washington for an AST review and managed to get out and catch the last 2 days of the conference. We're here mostly to present an idea for asteroid mitigation and some work we've been doing for the last couple of years. And it was a good opportunity. I didn't know the conference existed before I started this project, but it's a great audience for this kind of work. It's ideal.
And can you describe your concept? It's called the DE star system, and it's a laser-based system that could be used for asteroid deflection, correct?
It can be used both for deflection of asteroids as well as for direct evaporation of asteroids, amongst other uses. But it was initially designed to allow us to evaporate asteroids up to 500 meters in diameter completely in the course of approximately 1 year. So that was our sort of intellectual marching orders were, I said, here's our goal. Can we take some other things we've been doing and apply it at a much higher level? And is it feasible to do this? And so we set as a target 500 meters. We were looking at Apophis as a candidate, which is about 300 meters. Mm-hmm. And so it turns out that we set a baseline requirement of approximately 500 meters over a year, complete evaporation, not just deflection. So it was a worst case scenario, absolutely worst case. And then we decided that we'd like to begin to engage the asteroids, begin the evaporation process at greater than 1 AU. 1 AU is the mean distance, the average distance between the Earth and the Sun. So these are very large distances to do something like this at. But we set it as a goal to see if it was possible to do this, and that's what evolved into what you see here. The system is modular in the sense you can build small versions of it, not for taking out asteroids, but for testing. So it doesn't require you to build a whole system to validate it, which is one of the other things I wanted to do, is make sure that we didn't have to spend billions of dollars to build something and then find out that we made some mistake along the way. So we propose a system which is very logical and based on a number of existing technologies which are already very compelling. We don't require any technological miracle for this project, which was another requirement I had, that it should be something possible to do, even if difficult. And that we wanted it to be modular so that you could test it without spending a lot of money. And then work your way up and find out what the problems are and then solve the problems, or find that they're not solvable in the near term. But so far we haven't found any problems that are not solvable. But we do see technological challenges, but it does not require any completely new technology at this point. It does require a lot of engineering detail, and it does require us to be able to launch and mostly assemble large structures in space. The modularity allows you to send up subcomponents that then are assembled into the larger components. You don't have to send the whole thing up at once at all. You can send up very small things and robotically build it.
So this would be utilizing solar radiation, converting it into electricity, and then converting that into a laser-based system which could vaporize either the surface or potentially the entirety of an asteroid.
Yeah, so in a nutshell, the basic idea is that you want to form a spot on the asteroid and raise the temperature, the effective temperature of that spot high enough that all known elements will evaporate. And the way you do that is you have to have a system which is large enough, an optical system. We'll worry about the phased array part later. You simply have to have an optical system which is large enough to focus a beam at large enough distances so that it's intense enough to begin the evaporation process. And that requires surface temperatures at the asteroid of roughly 2,000 to 3,000 degrees Kelvin. So hot enough to vaporize almost all known elements. Some elements we have to get up into the 4,000 to 5,000 degree Kelvin. Things like, if you had a solid carbon asteroid or solid diamond asteroid, which would be that would be interesting.
Yeah.
Which nothing that we know of exists like that. But we have the ability to vaporize basically every known element. So once you do that, once you form a spot which is small enough and intense enough, then you have to ask yourself, how are you going to power such a system, and how much power do you need, of course. And the answer is that if you want to evaporate asteroids at about 1 EU or a little bit beyond, you need a system which is about 10 kilometers in size, between 1 and 10 kilometers in size. So 10 kilometers is 6 miles. So it's not a small structure. The International Space Station, for reference, is 1/10 of a kilometer in size, approximately 100 meters. This would be 100 times larger in each dimension. So, a formidable assembly project in space. Not impossible, but formidable. No, it's okay. So the question of power then comes immediately into play, because in order to do what we want to be able to provide approximately 70 gigawatts of laser power. And at the current efficiency of lasers, which is actually quite good. Lasers now, the type that we're using, are already close to 50% efficient, between 35 and 50%. There were some reports recently of 69% efficiency. They're already amazingly efficient. So there's not much room left to go on that front for efficiency. There are other areas where we need to improve. But the size of the system that is required to form the small spot also turns out to be just about the right size to be powered by the sun through converting sunlight into electricity via photovoltaics. So you don't need any other power source on board. You don't need any reactors, nothing else, just solar photovoltaics. And those two together give you a system which is capable of both powering the lasers and forming the spot on the asteroid to completely obliterate an asteroid, completely evaporate. Worst case analysis, completely bring it down to the atomic or molecular level, depending on the composition, so nothing's left of the asteroid except the vapor, which is in space. And that is clearly a worst case analysis. What actually happens along the way in the process of forming the intense spot, which begins the vaporization process, as you can imagine, if you're boiling a pot of water, the water vapor which is coming off the pot is actually pushing down on the surface of the water. Now, you don't notice it because it's a small effect. But in this case, the amount of thrust on the asteroid from the ejected material coming off the asteroid, which is therefore pushing back on the asteroid, just action and reaction, that thrust is approximately equivalent to the shuttle SRB, the solid rocket booster. Enormous thrust. So you don't have to vaporize the asteroid completely. You can certainly push it off course dramatically compared to any of the other existing technologies of using gravity tractors or putting small ion engines, which are a few pounds of thrust. Right. This thing puts on the order of 1 million pounds of thrust on the asteroid. So it's a phenomenal amount of thrust. And it's, anyway, that's one of the uses. Actually, when we started this, the other thing we wanted in such a system was not to only be able to interdict asteroids, to be able to go out and deflect them or vaporize them as needed, but we want something which would also be useful for other purposes, so that the money spent on it would be returned in other ways. So if you want, we could talk about that as well. But, we looked at spacecraft propulsion, for example. It turns out that the photon pressure on the reflector of a spacecraft is such that you could get roughly from here to Mars in approximately 3 days with a 100-kilogram class robotic spacecraft. So that's a small spacecraft, a couple 100 pounds.
So that's basically having this thing in orbit around the Earth and then
Correct.
beaming the power to the spacecraft?
Correct. So it pushes on the spacecraft, and because it pushes on the spacecraft continuously, it's not like in a chemical rocket. What normally happens in a mission, say to Mars or to the Moon, is you fire your chemical rocket to get off the Earth. Most of it's gone by the time you get up into orbit, And then if you want to go to the moon, you fire it for a little while, and you don't leave it on the whole time. You don't have enough fuel. Right. This system is on basically all the time if you want. So now there are issues, as we discussed earlier. What do you do when you get to Mars in such a system? Because it's going at a phenomenal speed. By the time it gets to Mars, for a 100-kilogram class robotic system, it's going over 1,000 kilometers per second. Wow. Amazing speeds. In fact, that's high enough to exit the galaxy. It's actually higher than the escape velocity of the galaxy. Wow. The solar system, you blow right through the solar system. Now, it takes a while to get out of the solar system, but you're going at phenomenal speeds compared to any chemical propulsion system that we have envisioned. So it has applications. I think the whole idea of propelling spacecraft via this technique is something to look at. You have to understand that you want to be able to do more with the spacecraft than just go past Mars. You want to actually orbit Mars and land. So as we discussed earlier, there are issues that one has to deal with in terms of how do you slow down once you get there. Do you carry an ion engine on board that you power from this thing? Because this is a phenomenal power source. You basically have left your power. You have a plug and a long power cord. Right. You don't have any mass in the power cord that you're dragging with you. So it has uses. If you think about anything where you want massive amounts of power, this might have some uses for that purpose. And the other,
like for example, if we picture the space shuttle, how much of the mass of the rocket you see leaving the Earth is actually the shuttle you want to get out to your location versus fuel you got to take with you to get up off the Earth and then to get out to your destination. So you're saying we could take that power source and not have to take it with us and be able to provide even more power throughout the whole travel process, correct?
Correct. And so there are applications where this is appropriate, and there are applications where it's not appropriate. So one has to carefully analyze where you would use this. But basically that's correct. If you calculate the amount of power in the shuttle solid rocket booster, so there's the two solid rockets on the side, they have approximately 10 to 20 gigawatts of power each. Now, we don't normally think about them in terms of power. We think about them in terms of thrust. But if you calculate the power, they're roughly 10 to 20 gigawatts. The power of this system is, in the baseline system for the DE Star 4 system, is 70 gigawatts of photon power. So it's not surprising then that you might conclude that the thrust equivalent that you might be able to induce on the asteroid would be comparable to the shuttle. Now, this does not have an optimal nozzle design on the asteroid. No one designed the nozzle on the asteroid for us. But we lose a factor of a couple there in terms of efficiency. But we still have very large thrust in the asteroid. So in terms of propelling a spacecraft, you don't use the thrust from the ablation of the spacecraft. You could. So that is possible. So there is a mode where you use the system to drive an onboard propellant, but not in the sense of a normal propellant. It's simply being used as a mass that you eject. In that sense, it's somewhat akin to an ion engine, except you don't need the power. You don't carry the power with you for the ion engine. You send it via this technique. And it has vastly higher power per unit area than the sunlight. So therefore, you don't need to carry with you such a large amount of say, solar panels with you on the spacecraft. So there may be some interesting applications there. We've been looking at some of those. Another one is to be able to look at the composition of asteroids by, basically starting the evaporation process. You then eject material. But in the ejection process, you have a very hot surface on the asteroid. And so you can see that hot surface through a telescope. And so you have a backlight, and you have material which is being ejected. And so we've been looking at the possibility of analyzing the ejected material. So this might be useful for people that want to mine asteroids. They'd like to know what is it made out of. So this is, as we sometimes call a standoff solution, might be a standoff solution for that, to determine the composition. You can also change the trajectory of asteroids. So if you want to harvest them, this allows you to do that in some applications.
What seems so incredible about this is you're talking about speed of light action, basically. So to go out and, just figure out what an asteroid's made out of, currently we'd have to send a whole mission out there. It would take a long time to get there. It'd be very expensive to build the whole system to get to it. Here you could have a capability already existing, and then from that capability, speed of light action, you could decide, I want to see what that one's made out of. I want to move that one around. It just seems like an incredible capability.
That's correct. So this is designed to be a multitasking system. Even it doesn't actually even have to point in one direction only. It can simultaneously send out different beams. Because it's a phased array. It can simultaneously send out essentially as many beams as you want. So you could be both propelling a spacecraft and analyzing composition of an asteroid and evaporating another asteroid and some other sending power to a lunar base. The way the system is built, it can do multiple things at once. But that's basically correct. What you said is that you're not taking with you your power system. You're leaving it at home, and you're sending it at the speed of light. So it takes approximately 8 minutes for light to get from the Earth to 1 AU, which is the amount of time it takes for sunlight to get to the Earth. And so you can, 8 minutes after you turn the thing on, you can begin to, intercept an asteroid at 1 AU. Similarly, you can, propel a spacecraft by using the light to push on the spacecraft, and you don't have to carry the propulsion system. But again, there are limits of this technology. You'd want to apply it appropriately, like any technology. But the interesting thing is we don't require a miracle to get this to go. Right? We don't need antimatter drives. We don't need warp drives. We don't need even fusion drives, although we hope that those will come someday. But using technologies which both exist now and are rapidly evolving, we can not only imagine such a system, but we can actually build small versions of this system and then work our way up to a final system, to a larger system.
Maybe one last broader question, because we're here at the 2013 Planetary Defense Conference, and there's a lot of discussion on the role of asteroids and comets impacting Earth and affecting life on Earth. There's also growing attention to space weather, for example, the role of solar activity potentially affecting life on Earth. And it seems like mankind more and more is being confronted that we're not just living on Earth. The Earth is a small part of the whole solar system. The solar system is a part of a galaxy. And if we're going to continue to progress and exist in these systems, we've got to be thinking about the solar system first, then Earth, broader pictures, then Earth. Do you have anything to comment on that view that mankind seems to be moving towards?
Yeah, I would hope we could put aside our petty squabbles and truly deal with things which are meaningful in life, and working together to go out and place ourselves on the moon as a near-term mission. Some have a base on the moon. Is a laudable mission to do the same with Mars, and then to work our way out. Hopefully, eventually we could get out of the solar system. One of the things that so I draw the distinction sort of between things which are realistic to come to fruition, say in a lifetime, versus those things which are perhaps several lifetimes out. And so one of the things is you could ask yourself, suppose you go further than simply wanting to deal with asteroids or propel spacecraft in our solar system. What could you do? So if you step up and you ask, what would happen if you scaled this up even larger? Could you build a system which could propel a spacecraft to the nearest stars? And so we spend some of our time in our papers looking at this issue. And you can, in theory, and I'm not saying this is practical at the moment, it's not, but if you follow the same evolutionary approach, again, you don't need new technology here. You need to be able to assemble things in space which are very large. So that requires an evolutionary approach to our ability to both launch and assemble in space. So those are areas that we need to work on. But if one scales up, you can conclude that if you go to a DE star 6, you can then propel a 10,000 kilogram spacecraft, which is basically 10 tons, at near the speed of light, not at the speed of light, near the speed of light, so that you could imagine an interstellar probe someday, without warp drive, without fusion drive. Now, we have the same problems. What do you do when you get there? How do you slow down? Because you're going real fast. But it brings up some fascinating possibilities. I wouldn't advocate sending people there in the beginning, send out robotic probes, but I am very much an advocate of sending out probes into not only the solar system, but beyond. And we can decide what we want to do with those probes. But I think what you said before is key to one of the differences between this and other approaches. In many of the other approaches in dealing with asteroids, one sends a mission to an asteroid to deflect the asteroid. One sends a mission to analyze the material. One sends a mission to put on an ion engine on the asteroid to, change its orbit. In our approach, we don't do that. We stand off, and we start by we just stay at the Earth or on the Moon or at the Lagrange point, the different places you could put this. And we say, let us, use the fact that we can travel with our energy at the speed of light to the object, and let us work on the system that way, rather than having to mount a mission to every asteroid we think might be a threat.
Right.
And the great advantage is here, and I think in the long run, if you do the analysis, you probably figure out this is a much cheaper way to do it.
Absolutely.
Because you don't have to launch a mission which using chemical propulsion systems can take years to get to an asteroid. And then, what do you do when you get there? So this is a different approach altogether.
Well, I appreciate you taking the time to explain this interesting concept for us. I don't know if you have anything else you'd like to add?
No, I think maybe one way for those of you that are watching this to think about things that are related to what we're doing. If you go into the hardware store and you look at an LED light bulb and you ask yourself, what went into this LED light bulb and why is it so much better than an incandescent light bulb? And why should I buy this light bulb versus compact fluorescent or an incandescent? Well, I agree. At the moment, the choice between buying a compact fluorescent and buying an LED is a tough choice because it's an economic choice. But the economy of that is changing very rapidly. The same technological revolution, the same photonics and electronic revolution, which makes the LED possible in your little, there's a light somewhere, I don't know. There's an LED somewhere around here.
Sure.
In your PowerPoint laser pointer, in your LED light bulb, in your flashlight, in your LED light bulb that you buy for your home. That same technology is, in fact, what's driving the possibility of making this a reality. It's the conversion of electricity into light at high efficiency. And that has now gotten to the point where one can not only envision something like this, but one can begin to build something like this.
Well, it's very exciting. Thank you very much.
You're very welcome. Thank you very much.